Hi and welcome back to my channel. So in previous few videos I've been playing with this mixer. Okay, so this mixer is just this can here, this seal can. The model is I don't know if you can read, but MCL SRA1 from Mini Circuits. So I just soldered this on this copper plate and connected it to 3 BNC plugs to experiment a little bit. And in my previous episode, number 28, I used the HackRF to drive the local oscillator port of the mixer. Okay, the great thing about the HackRF is that it can generate signals from 1 to 6 gigahertz. So in theory, I can drive the mixer with a local oscillator up to 6 gigahertz. So now this specific mixer that I've been using is not good for 6 gigahertz. It only works up to 500 megahertz. But as you can see here in this list, there are a lot of mixers available just from this company, Mini Circuits, and there are many other companies, of course. And you know, each of them has different characteristics. For example, I don't know, this randomly chosen one here. It can down convert to baseband, so from DC to 1.5 gigahertz, signals that are between 1 and 4.2 gigahertz. Okay, so one application, for example, that I have in mind, I would like to use the HackRF with a mixer, not this one, but another one, is to extend the possibilities of my spectrum analyzer. So this spectrum analyzer can only scan from 0 to 1.8 gigahertz, so I cannot, for example, see what's going on the 2.4 gigahertz where Wi-Fi or Bluetooth are. So the idea would be to use a mixer to down convert the 2.4 gigahertz band, for example, to 1.4, where this spectrum analyzer could look at. And for that I would need a mixer and a signal generator here, like the HackRF, capable of producing 1 gigahertz, you know, because we are getting a shift of 1 gigahertz from 2.4 gigahertz to 1 gigahertz, 1.4 gigahertz, so just 1 gigahertz shift. However, each of these oscillators, as you can see here, for example this one that we considered, has a specification called the LO level, the local oscillator level. So the mixer works well if you can provide the signal, the local oscillator signal, at 7 dBm. So you can see there are many different levels, but 7 is very common, also 10 or 17 are very common. Just a few have something below 7. So let me order this list by the local oscillator value. And so as you can see, they offer only 3 mixers with local oscillator value below 7. So 7 is kind of the standard. I mean, it's for this type of mixer, this double balance mixer. And so this means that it is required for the mixer to work together with the HackRF, that the HackRF can provide at least 7 dBm as a local oscillator. So in this video I'm going to test what are the capabilities of the HackRF as a signal generator with my spectrum analyzer. Of course I can only check the strengths of the signal generated by the HackRF up to 1.8 gigahertz. Okay, so if you're not interested in watching the whole video to follow the measurement precisely, just have a look in the description below where I will include the final results. Instead, if you're interested, please continue watching. Okay, so here you can see the spectrum analyzer on the top right corner of the screen, and my HackRF here. This is of course the PortaPack extension of the HackRF with the Havoc firmware. So let me start, and so I click here, I go to utilities, I hope you can see, and utilities, not settings, and utilities there is the application called signal generator, so let me click that. In this application I configure here the shape of the signal to be a sinusoidal function, the tone to be transmitted to be 0 hertz, so not 2 hertz, 0 hertz, So this signal generator is an FM modulator, okay? So if we modulate no signal, so 0 Hertz, we are going to get just one stable frequency at the carrier. The carrier is set here. So for example, here at the moment we have 30 megahertz. Here we can set the level. At the moment is set at 47, which is the maximum. And the bandwidth is irrelevant since we are not modulating any tone. Okay, I'm going to click here auto, so the modification that I make will be activated immediately on the fly by the signal generator, and so I'm ready to start now. Before I start, let me change the amplitude of my spectrum analyzer to 40 dB. So this is something useful. Where is it? dB here. Okay, as you can see, this increases the noise floor, but it's better to check out the harmonics because, you know, if without the attenuation, the spectrum analyzer would be kind of overloaded by the maximum strength of this HackRF, and so some reading on the harmonics could be not precise enough. Instead, with an attenuation of 40 dB, we get the best readings. Anyway, so let me reduce a little bit the reference level. So now we have at the top of the screen we have 20 dB, and let me put a line at 7 dBm. Okay, so what is it? So why the line is saying? So yeah, okay, I could not see. So 7 dBm is here. Okay, perfect. So our goal for working with mixer requiring 7 dBm for the local oscillator is to be able to reach that line. Okay, so I'm going to start with a 30 megahertz signal, and so let's see what is the response. So start. Okay. So as you can see, we are getting above the desired 7 dBm. In fact, we are getting the main carrier is at 14, so mission accomplished. Let me reduce a little bit the gain until we get precisely to 7. So 7.5 or something like that. That's fine. And let me measure the harmonics at this level. I will do this for all the frequency along the experiment. Okay, so let me measure the harmonics. So let me zoom in a little bit. So 100 megahertz. Sorry, center frequency. So start frequency, let's put 10 megahertz, and stop frequency 100 megahertz. Okay, so our carrier is at 7 dBm, as we said, and instead the first harmonics is at minus 18. So this means an harmonic rejection of 25 dB. Okay, so the first harmonics is 25 dB below the main carrier. Okay, perfect. So let's move now the experiment to another frequency. So let me set again central frequency. Well, let me put it now 200 and the span at 400 megahertz. Okay, so I'm going now to try with 100 megahertz. So let me insert 100 here. Done. Okay, so at the moment we have oh yes, span of let's say 400 megahertz. Okay, so we have our signal here at 100 megahertz, but as you can see, it's not right at the. So let me disable here. The delta marker that we had before. So with the same gain setting as before, we are only getting about 1 dBm at the moment on this 100 megahertz. So let me increase the gain until we reach the desired 7 dBm, if we can reach it. Yeah, it's more or less here. Perfect. And I'm going to measure the difference with the first harmonics. And in this case, it is at 27. Okay, so the harmonic rejection is at 27 dB down. Okay, so let me go back to normal market, and finally let me see what is the maximum power at this level, and that's this is 9 dBm at 100 megahertz. Okay, excellent. So let me move on with the experiment. So let's say 500 megahertz. I'm now going to try with a frequency of 200 megahertz. So 200 megahertz, done. Okay, so our main signal at the moment is so we are already at the maximum, so the HackRF cannot output more than this, and unfortunately we are only at about 4.5 dBm, so the HackRF could not reach the desired 7 dBm in this case, unfortunately. And let me see, the first harmonics is 26 dB down. Okay, so let me move the experiment to stop frequency 1 gigahertz. So I'm going to move the experiment now to the frequency, let's say 500 megahertz. So okay, so let me actually stop frequency 1.2 gigahertz, so we can see the full first harmonics. Okay, so again the peak now is, unfortunately we are at maximum power and the peak is only 1.5 dB. So that's not sufficient, unfortunately, for driving the mixer properly. And the first harmonics is at 21 dB down. So even the harmonic rejection is becoming less good at this frequency. Okay, so we are at 500. Let's move now, so stop frequency 1.8 gigahertz, so the maximum. And let's move now to 1 gigahertz. So 1000 megahertz. Okay, so again we are at the maximum, the HackRF, and we are getting barely 0 dBm. In this case, as you can see, well, this is not the harmonic. So the next, oops, sorry. So this other signal that we have here is not the harmonics, it's not at 2 gigahertz, this is 1.3, and is probably a reflection of, I mean, as an artifact of the spectrum analyzer, this is a reflection of the 2 gigahertz that we should see, but cannot be seen because the spectrum analyzer stops at 1.8. Anyway, in this case I cannot properly measure the harmonic rejection. So anyway, let me move on in the frequency just to see what is the main strength at higher frequency. So for example, 1 gigahertz and a half, and yes, so 1500 megahertz, and it's at minus 4 dBm, so again not good enough for driving a mixer, a 7-level mixer. And okay, let me try finally with the maximum frequency that I can read, which is 1.8 gigahertz, so 1800 megahertz. So frequency 1.8 gigahertz. So that's wait, oops, frequency and cal. So let me see frequency. So let me actually reset the spectrum analyzer. He kind of didn't like what I did there. So config, let me, okay. So yes, we have our signal there, as you can see. Peak search, and it is saying at 1.8 we only get minus 3.5 or something dBm. So yeah, unfortunately this HackRF, at least my model, cannot produce sufficiently strong signals to drive a mixer. So this concludes my analysis of the maximal strength of the signal of the HackRF. But it's not a conclusive analysis because I could only verify signals up to 1.8 gigahertz. And in fact, the official data states that the maximal power is usually reached between 2 gigahertz, 150 megahertz, and 2 gigahertz, 750 megahertz. So there is still hope that these frequencies, the HackRF can produce the desired 7 dBm. Here the specification seems to suggest that this is the case, but I have to say from 0 to 1.8 I couldn't verify really these values, so we saw that generally we get signals below 5 dBm, so at least my model cannot achieve these performances. But anyway, it would be great if somebody else with the means, for example, better spectrum analyzer with a larger span up to 6 gigahertz, for example, could verify also the strength of the HackRF at these frequencies. That would be great. In case you discover something, please let me know, and for example, writing in the comment section below. And that's it. That's all for this video. Bye bye. See you next time.